Hello. This is Nicholas, and I am doing a video on exact differential equations. I want the exact differential equations. They arise from the question. They arise from level curves, basically. And so level curves, if we consider a multivariable function. So this is from the other video. Let's say we have f of x, y. Then the set of level curves, I'll just call L of x, y, is just all the places where f of x, y equals some constant. So in other words, it's cross sections, all right? It's cross sections of this multivariable function when the whole function is just set equal to some constant. What level curves, and they would be two-dimensional level curves, in other words, planes, since the function is three-dimensional. In general, the level curves are just one dimension less than the function itself. So level curves actually provide a good way to visualize, at least kind of, four-dimensional functions. In other words, functions of the form w equals f of x, comma y, comma z, because the level curves are in 3 dimensions. They would be a three-dimensional cross-section. Kind of hard to wrap your brain around there, but a four-dimensional sphere, if you were to pass it through our three-dimensional world, its cross-sections would be the three-dimensional spheres that we're used to. Just like how if you were to pass a 3D sphere through a 2D world, the cross-section would start out as a point and then go to a line, and as a point, a line, it would grow into a circle, and then it would shrink and then back to a point. And the question is, how do we calculate the slope of a line tangent to a level curve? Well, obviously we would have to take the derivative with respect to x of both sides. That's all about. The slope is the derivative. So now the derivative of a multivariable function. So we're assuming that this function f, it's got two variables. It's got x and it's got a y. But we're assuming, of course, that y is a function of x. So y takes us to x. It's defined implicitly, just like how we did implicit differentiation in Calc 1. So, and if you're aware of the multivariable chain rule at all, the idea is basically, these tree diagrams are very helpful. I use them. It's basically saying anywhere you've got a branch, that's a partial derivative, where you can go either way. See, from f, I could either go to x or I could either go to y. So, and since there's two different ways, there's only one way you can go. So you're only partially going you're only going in one direction, not all directions. So it's just a partial derivative since it's only in one direction. So this derivative would be the partial of f with respect to x. That's this first bit here. Now, plus we add, because there's a new direction we could go. We could go from f to y. This is partial f with respect to y. And then as we go down the tree, see now dang, I knew that would happen. X. Now as we go down the tree, now we're at y. We're at y. And then there's only one way to go from y, since we've already started at f. There's only one way to go from y, and that's to x. So when there is no other way to go, you just multiply. So, and since we are now, since y is just a function of x, it's no longer a partial derivative anymore. It's just dy over dx, because the partial derivative of y with respect to x would be equal to dy over dx, since it's not a multivariable function. It's just single variable. And the derivative of a constant is 0. So, and by the way, I just want to say this. If you do solve this formula for dy over dx, it means that dy over dx is negative, I'll write it as, this is another way to write it, the partial derivative with respect to x over the partial derivative of f with respect to y. And so this is a very nice formula for finding dy over dx implicitly. It works out very nice. Maybe just a quick example of that, because it is pretty cool. If I have x squared y cubed minus, say, 6y plus 7 sine x equals 0, and it does have to be set equal to 0 on the right side, but you can always do that, just move everything over to one side. Then what dy over dx would be, it would be negative of the partial derivative with respect to x, so that's 2xy cubed, 6y is a constant with respect to x, so that's 0, plus 7 cosine x, over, now with respect to y, that's 3x squared y squared minus 6, and sine x is a constant. So that right there is the dy over dx, and no implicit, well, it is implicit differentiation, but it's a lot easier than using the product rule here, and then here another dy over dx, and then solving for dy over dx. It just gives you it right off the bat, boom, like that. That's not really what this video is about. I just wanted to give an example. Now, if I were to take this here and multiply by a dx, I would get that partial f with respect to x times dx plus partial f with respect to y times dy is equal to 0. And this is known as the total, from calc 3, the total differential of f. So now, exact differential equations, they are in the form m of xy dx plus n of xy dy equals 0. And so why did I go through this total differential business? I went through it because if you compare coefficients here, then it should really be obvious that m of xy is nothing but the partial of f with respect to x, where this capital F here is the solution to the differential equation, because after all, we just took the derivative of f, now we're just undoing it. And likewise, n of xy is partial f with respect to y. And so the solution, since we started out with this, and now we're at this, sorry, since we started at capital F of xy equals c, then our solutions will be in the form f of xy equals c, since that's how we started out to begin with. We started off with differentiated it. Now we're trying to work backwards. So solutions are in the form f of xy equals c. And so if you are familiar, more multivariable calc, if you are familiar with Clairaut's theorem, which says that if you have a function, say f, and a function g, and they're multivariable, and if f and g are continuous, and the partial f with respect to x, the partial f with respect to y, the partial g with respect to x, and the partial g with respect to y. If all those things are continuous, then their mixed partials are the same. So what this means is that if I take the function f, and the way they write it as, okay, I'll write it like this. If I were to take the function f, the partial derivative of f with respect to x, and then take that partial derivative with respect to y, then by Clairaut's theorem, it should be equal to the partial with respect to x of the partial of f with respect to y. In other words, it doesn't matter which order I take the partials in. it can be either with respect to x, then with respect to y, or with respect to y, and then with respect to x. Doesn't matter which order I take them in. I'm not going to do a proof about that on this video because that's not what this video is about. It's about solving exact differential equations, but there are a number of proofs about it in any Calc 3 book. It'll give you a proof. And a more common way to write this is that f of xy is equal to f sub yx. That's just another notation. And I don't like the notation because really you're putting parentheses here. And it looks like you're taking the partial with respect to x, then with respect to y. But it means exactly the opposite, actually. So I think the notation's a little confusing. Anyway, you can generalize Clairaut's theorem by, hopefully you would guess that it would also, this is a generalization, it's that f of x, y, so 3 partial derivatives there is equal to f of x, y, f sub x, y, x is equal to f sub y, x, x. And you could probably guess where it's just any combination of x and y, basically. That's where the mixed partials are the same. So now, let's actually do an example of a exact differential equation. And so I do just want to say before that, so this right here is how you can actually test for the exactness of a to see if a differential equation is actually exact or not. So if this condition is true, in other words, the function and its partial derivatives are all continuous, which we would want it to be, then this should be true, and so the equation will be exact. An example now, if we have tangent of y minus 2, this is parentheses, tangent of y minus 2 dx plus x secant squared y plus 1 over y dy is equal to 0. So right off the bat, I know that this piece right here is the partial of f with respect to x, where f is the solution to the equation, and this is the partial of f with respect to y. So first I want to check for exactness. So the way I remember it is I say, well, this goes with the x, so I need to partially differentiate it with respect to the y, and this is with the y, so I need to differentiate this with respect to x. So in other words, I need to first take the partial with respect to y of the tangent of y minus 2, which is just secant squared of y. Now I need to take the partial with respect to x of x secant squared y plus 1 over y. And this is also secant squared y. So since the mixed partials are continuous, the differential equation is exact. Now here's the way to go about it. We can pick this or this. And what we're going to do is I'll pick the first one. Doesn't matter which one you pick. In fact, I would encourage you to pick the one that I don't so that you can try this out for yourself. Let's pick the first. Partial f with respect to x is the tangent of y minus 2. And this is actually a partial differential equation. And so to solve it, it's a separable one. It's really easy. Just integrate both sides, right? With respect to x. So, and be careful here because now we're treating y as a constant. So we're treating y as a constant. So the partial with respect to x, after we do the integration, is x times the tangent of y minus 2x plus f of y. Now, why did I write f of y and not just plus c? I wrote that because when we're partially differentiating with respect to x, any function of y is treated as a constant. So a function solely in terms of y is the same function as adding a constant. And so that's why I add the f of y. So this is f. This is our function f. But we need to find what this little f of y is. So what we can now do is we can differentiate, we can take this f and we can now differentiate it with respect to y. So partial f with respect to y should be x secant squared y plus f prime of y. And remember, partial f with respect to y is also this. Oops, I drew over, is this. So we set this equal to x secant squared y plus 1 over y. And get rid of that. So f prime of y is 1 over y. So f of y is natural log of y plus the c. So our solution is of the form f of xy equals c. So our f of xy is x tan y minus 2x plus natural log of y equals c. And that's the solution to this exact differential equation. And I could have started out with partial f with respect to y here, and then integrated and then taken partial f with respect to x. You'd get the same answer both ways, and in fact, I'd encourage you to do it the other way to make sure that we get the same answers. But this is basically the idea with exact differential equations.